Welcome to this in-depth scientific lecture on time-crystalline behavior in driven solid-state nanostructures, a frontier topic in quantum many-body physics. Time crystals represent a remarkable phase of matter, where quantum systems exhibit periodic motion in time, seemingly violating thermodynamic principles about ground states. Let us begin by reviewing the thermodynamic principles that time crystals appear to challenge. In classical thermodynamics, the ground state of any system is the lowest energy configuration, which must be static and time-independent. The ground state, psi-0, satisfies the eigenvalue equation, where the Hamiltonian H gives the minimum energy E0. At absolute zero temperature, the expectation value of any observable O is time-independent in the ground state. This graph shows how systems evolve toward a static ground state at zero temperature, with energy decaying to a constant minimum value. This raises a fundamental question. Is it possible to have persistent motion in a quantum system without continuous energy input or heating? The answer is yes. Through time crystals and periodically driven quantum systems, motion can persist without net energy absorption. To understand time crystals, we must first understand discrete time translation symmetry in driven systems. When we apply a periodic drive to a quantum system, we create a discrete time translation symmetry rather than continuous time symmetry. The time-dependent Hamiltonian h of t equals h of t plus t, where t is the driving period. We can decompose this into a static part h0 plus a time-dependent driving term hd of t. Here we visualize a periodic drive with period t, creating discrete time translation symmetry in the system. We use Floquet theory to analyze these periodically driven quantum systems, which is analogous to block theory for spatial crystals. The quantum state at time t plus t equals the Floquet evolution operator UF times the state at time t. The Floquet operator is the time-ordered exponential of minus I over h bar times the integral of h over 1 period. Now we arrive at the key concept: spontaneous breaking of discrete time translation symmetry. In a discrete time crystal, the system spontaneously breaks the discrete time symmetry by responding with period 2t or even higher multiples of the driving period t. For a period doubling time crystal, the expectation value of an observable at time t plus t equals minus the value at time t. But at time t plus 2t, the observable returns to its original value, completing the period doubled cycle. This graph illustrates the driving signal with period t in red and the system response with doubled period 2t in green, showing spontaneous symmetry breaking. You might wonder, does this period doubling violate energy conservation? How can the system respond differently than driven? The answer is that the system is in a many-body localized state that absorbs zero net energy averaged over many drive cycles, avoiding thermalization. Let us examine the first solid-state implementation using nitrogen vacancy centers in diamond. Nitrogen vacancy centers are point defects in diamond consisting of a nitrogen atom next to a vacancy with an electronic spin-1 ground state. The NV Hamiltonian includes zero field splitting dsz squared, Zeeman coupling gamma bsz, and a driving term. This diagram shows an NV center with the nitrogen atom in green, the vacancy in red, and surrounding carbon atoms with microwave driving. Typical experimental parameters include zero field splitting d equals 2.87 GHz and microwave driving frequencies in the megahertz range. The driving frequency omega drive is typically between 1 and 10 MHz. This gives driving periods t drive of approximately 100 nanoseconds. Time crystals emerge in arrays of coupled NV centers, not isolated spins. Dipolar magnetic coupling between neighboring NV centers creates the many-body interactions necessary for collective time-crystalline behavior. The interaction Hamiltonian includes the dipole-dipole coupling between spins I and j, falling off as 1 over r cubed. This shows a two-dimensional array of coupled NV spins, with dipolar interactions represented by the connecting lines. For typical NV spacing of 10 nanometers, the dipolar coupling strength is approximately 10 kHz. This coupling J equals mu0 gamma squared h bar squared over 4 pi times 10 nanometers cubed, giving roughly 10 kHz. Many-body localization is crucial for stabilizing the time-crystalline phase against thermalization. Strong disorder in the spin array prevents the system from reaching thermal equilibrium, a phenomenon called many-body localization. The disorder Hamiltonian includes random on-site fields, HISIZ, at each spin site. These random fields, HI, are drawn from a Gaussian distribution with zero mean and variance W squared. This shows the Gaussian distribution of disorder fields, with individual spin realizations shown as vertical bars. For many-body localization to occur, the disorder strength W must exceed the interaction coupling J. When W is greater than J, the system enters the many-body localized phase, preventing thermalization. A critical question is how many-body localization prevents the driven system from heating up indefinitely. MBL breaks ergodicity, meaning the system retains memory of its initial state and cannot explore the full Hilbert space to thermalize. Combining Floquet theory with many-body localization gives us the framework for stable time crystals. Floquet many-body localization extends MBL to periodically driven systems, preventing energy absorption over many drive cycles. The average energy at time nt equals the initial energy plus epsilon times n, where epsilon is exponentially small in system size. The heating rate epsilon scales as exponential of minus L over xi, where L is system size, and xi is localization length. This graph compares energy growth over drive cycles. Floquet MBL shows negligible heating in green, while thermal systems heat linearly in red. In typical experimental systems, the localization length LE is approximately 5 to 10 lattice sites. The localization length LE is roughly 5 to 10 times the lattice spacing A. Let us examine how experimentalists actually observe time-crystalline behavior in the laboratory. First, initialize all spins in a highly polarized state with initial magnetization M0 along the z-axis. The initial state is the tensor product of n spins, all in the S-Z equals +1 state. Apply periodic pi pulse rotations with period t drive, flipping all spins around a specified axis. Each pi pulse is the unitary operator exponential of minus I pi sx, rotating spins 180 degrees about the x-axis. This shows the spin flip sequence. Spins alternate between up and down states with each pi pulse, forming the basis for time-crystalline response. After each pulse, measure the total magnetization m of t to track the collective spin dynamics. The magnetization m of t equals 1 over n times the sum of all spin expectation values SIZ at time t. Finally, analyze the Fourier transform of the magnetization time series to identify period doubling or higher harmonics. The Fourier transform m tilde of omega is the integral of m of t times exponential I omega t over the measurement time. What are the key experimental signatures that distinguish true time crystals from trivial periodic dynamics? The primary signature is a sharp peak in the Fourier spectrum at frequency omega equals pi over t, indicating period doubling. The power at omega equals pi over t greatly exceeds the power at the drive frequency 2 pi over t. This Fourier spectrum shows the dominant subharmonic peak in green at half the drive frequency, with the drive frequency peak in yellow much weaker. Time crystals are robust to perturbations. Changing the pulse angle from exactly pi, or varying the period slightly, does not destroy the phase. Even when the pulse angle deviates from pi by delta theta up to 10%, time crystalline order persists. The system exhibits long-range temporal correlations that persist for hundreds or thousands of drive cycles. The temporal correlation function C of t and t prime remains significant even when t minus t prime is much greater than the drive period. Trapped ions provide another powerful platform for realizing time crystals with high control and long coherence. In trapped ion systems, laser-cooled ions form Coulomb crystals, where they are held in place by electromagnetic fields and interact through Coulomb repulsion. The effect of Hamiltonian includes local Zeeman splitting omega 0 and long-range Ising interactions Jij between spins I and J. This shows a linear chain of trapped ions with laser addressing from above and Coulomb interactions linking neighboring ions. Unlike short-range models, trapped ions exhibit long-range interactions, where Jij decays as 1 over the distance to the power alpha. The coupling scales as J0 over distance to the alpha, where alpha ranges from 0.5 to 1.5, depending on trap parameters. Trapped ions offer extremely high-fidelity quantum operations and coherence times exceeding seconds, enabling observation of many period-doubling cycles. Coherence time T2 is greater than 1,000 times the driving period T-drive, allowing thousands of cycles to be observed. Superconducting qubits and lattice geometries provide yet another platform with fast operations and scalability. Superconducting transmon qubits are coupled capacitively or through microwave resonators, forming two-dimensional lattice structures. The Hamiltonian includes qubit frequencies omega-I and nearest neighbor coupling Gij with raising and lowering operators. This depicts a square lattice of superconducting qubits, with nearest neighbor couplings forming a two-dimensional quantum spin network. Typical qubit frequencies in superconducting qubit lattices range from 4 to 8 GHz. This frequency range is suitable for exploring time-crystalline phenomena in these systems. In conclusion, time crystals represent a fascinating area of research that challenges traditional notions of thermodynamics and equilibrium. Time crystals exhibit spontaneous breaking of discrete time translation symmetry, giving rise to robust and long-lived oscillations. Many-body localization is essential for stabilizing time crystals, preventing the system from thermalizing and destroying the time-crystalline order. Experimental platforms like NV centers, trapped ions, and superconducting qubits provide a means to realize and study time crystals in the laboratory. Future research directions include exploring time crystals in other systems, such as optical lattices and topological insulators. Additionally, researchers are investigating potential applications of time crystals in quantum computing and metrology.